Today we're looking at our 8182 quiz for FST, again working with radical functions. We'll start by graphing this cube root function and also make sure you remember to find the domain and range. And actually, since I'm mentioning it, I may as well do that now. The domain for all cube root functions is all real numbers. So in interval notation, we just say that that's from negative infinity to infinity. And the range for cube root functions is the same. It goes from negative infinity to infinity, in other words, all real numbers. Alright, so talking about graphing this, again, we want to use points that will plot easily. And so what we're looking for is values of x that cube root nicely. So I will generally use these same 5 x values for each of these. Now notice I am just looking at the cube root of x, so what I'll have to do is come up with these points, and then because of the plus 3 here, again that's outside of the radical, so I'll take these points and shift them all up 3. So negative 8 gives me negative 2, negative 1 gives me negative 1, 0 is 0, 1 is 1, and 8 is 2. Again, that's just cube rooting those. It really simplifies the process if you just look at the cube root of x. So I'm going to zoom in a bit more, try to get kind of close to this graph. Let's see, so negative 8 was negative 2, so that's about there. Negative 1 was negative 1, 0 was 0, and 1 was 1, and then all the way over to 8 to get to 2. Now what we're going to do is again move those up 3. So instead of negative 8, negative 2, it's negative 8, 1. Negative 1 becomes negative 1, 2. You get 0, 3, and 1, 4. And then all the way over at 8 gives us 5. So we draw our curve through those points. Again, being careful in the middle there. And again, I'll label these final points here. We've got negative 8, 1. Let's see, negative 1 was 2, 0 was 3, 1 was 4, and 8 gave us 5. So those are the final points that I'd be looking for on that graph. And again, remember, we did the domain and range earlier. For number 2, we're looking at a square root function. Notice the minus 2 is inside of the radical. That means that that's going to provide a horizontal shift from our kind of regular square root of x function. Similar to the cube root, I typically use the same points, 0, 1, 4, and 9 for x, because those are, again, those first numbers that are easy to square root. Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, and square root of 9 is 3. Now because of the minus 2, what we do with those points is we then shift those right 2. Again, what happens there is the minus 2 is making those x values kind of happen later, and so that's why it's moved to the right. Let's see, so if we can look at those originals, we'd have a 0, 0, 1, 1, 4 is 2, and 9 is 3. Now, taking and moving those right 2, we get 2, 0, we get 3, 1, 6, 2, and then it would be 11, 3. So just, again, you can imagine that we went one further on the grid there. And we draw our curve through those points. The point here, in this case it ends up at 2, 0, is an end point. That can help you to determine your domain restrictions. So again, domain is all of your x values. Our x values, we don't have anything to the left of 2. So our domain is really all values of x that are greater than or equal to 2. So in interval notation we say that goes from 2 to infinity with the bracket to show that 2 is included. The range, likewise, doesn't go below that point at 2, 0. So the lowest that gets is 0. So So similarly, the range is limited, but it goes from 0 up to infinity. And so that's domain and range for that one. Alright, so then we move away from graphing and we're looking at simplifying roots. So something like a negative cube root of x to the sixth. Again, I'm going to change this to rational exponent form because I think it's easier to look at then. This would be x to the 6/3, and so that works out perfectly because 6 divided by 3 is 2, so we get a negative and then x squared. So that's all that looks like. Moving on to number 4, we have the cube root of x to the 9th. So again, if I switch that to rational exponent form, we get x to the 9/3, which would be x to the 3rd power, and then and that's it, really. That's all there is to it. Now, number 5, I want to emphasize actually the next set of directions where it says assume all variables represent positive real numbers. We're not assuming that here for number 5. So we have a square root of x to the 6th. So I want to make the point before I even simplify that again, whether x is positive or negative, you're going to take that x to the 6th power. So that even if x is negative, you take that to the 6th power, it's going to become positive. And we have the square root of that, so then that result will also be positive. So no matter whether x is positive or negative, or even 0, the result of this cannot be negative. Now if we simplify this, we get x to the 6/3, or sorry, 6 halves. I was thinking of the answer there. So 6/2, which ends up being x to the 3rd power. Now if we look at x to the 3rd power, if x is negative, like say for example x is a -2. -2 to the 3rd power would be -8. So in order to remedy that, we include absolute values here. And I like to just kind of analyze that at the end to see if they're necessary. Certainly, anytime you go to simplify an even root like that, you really should have that in absolute values. Sometimes it's not necessary, so I like to just kind of figure that out at the end, again, to determine whether those really need to be there or not. Now as we move to number 6, again, we are going to be assuming that all variables represent positive real numbers, which again means then that we don't need to worry about absolute values. For number 6, all we're trying to do here is write this with radicals, so switch that 1/9 power into a 9th root. So a 9th root of x squared y squared, and that's all there is to that one. For number 7, same thing, just write it in radical form. So it's to the 2/3 power, so it would be a 3rd root or cube root of 9m plus n squared. Now you can write it like I have with the squaring inside the radical, but still needing parentheses around the 9m plus n, or you could do the cube root of 9m plus n, put that in parentheses, and then square the whole thing. So 2 ways to write that. Here, again, we're still assuming all variables represent positive real numbers, but simplifying. Now, our radical properties aren't going to work here, so we're going to convert to rational exponents. They even tell us to do that. So, rational exponents here, we'd have w to the 1/7 times w to the 1/2. Now, back to our properties for exponents. When we're multiplying w's together, the way that we simplify that is we add the exponents. So we're adding 1/7 and 1/2 together. Now, your calculator can do that pretty well. If you're going to do this by hand, the least common denominator would be 14. So we'd have 2/14 for 1/7 plus 7/14 for 1/2. And so we end up with 9/14. Now they mention, again, simplified by first converting to rational exponents. They don't say to necessarily write the answer as a rational exponent, so my rule of thumb is if it starts in radical form, that's how we should end it. And so really for my answer there, I'd have the 14th root of w to the 9th power. So then we'll move on to number 9. Same sort of idea, a little bit different setup, but if we switch to rational exponents again, we would have v to the 3/5 power over v to the 3/8 power. Now, in this case, again, with a quotient of powers, we subtract the exponents. We have 3/5 minus 3/8. Again, your calculator can do 3/5 minus 3/8, otherwise the least common denominator would be 40. So 3/5 would be 24/40, and 3/8 would be 15/40. And so we find our difference there to be 9/40. And again, they didn't tell us to write our answer as a rational exponent, and we started with a radical, so we should end that way. So let's say 40th root of v to the 9th power for that. All right, moving on to number 10. Again, they just mentioned we're using the rules of exponents to simplify. They do want the answer written with positive exponents, and we're still assuming that all variables represent positive real numbers, so we don't have to worry about absolute values in these cases. So starting with number 10, b to the 4th to the 7/4 power. So this is a power of a power. So that tells us that we multiply the exponents together. In this case, a 4 times a 7/4 is just 7. So it works out pretty well there. Let's see, moving on to number 11. Now we do have some negative exponents here. So you end up with some choices as far as how you want to simplify this. You could use the negative exponent property to drop that z down to the denominator. However, looking at the fact that we have a z to the negative 2/5 and a z to the 3/5, I would probably go the route of just applying the product of powers property, which says that when we're multiplying powers together, we just add the exponents. So we would add negative 2/5 to 3/5, this again, especially seeing that they're already fifths, and we end up with z to the 1/5. And we started in rational exponent form, so we certainly can leave it there. Z to the 1/5 is perfectly fine. Looking at number 12, we've got a fraction to the 1/4 power. Notice though that y to the negative 8th is in the denominator. So in this case, I would probably choose to use that negative exponent property to bring that y to the 8th up to the numerator, and then just take that product to the 1/4 power. So again, there's really two properties we're using here. It's the power of a product property. So we take the x to the 4th to the 1/4 power and the y to the 8th to the 1/4 power. Parentheses are really just for emphasis. And then the power of a power property, which says we multiply the exponents together when you have a power of a power. Well, that ends up just being x to the 1st power, because 4 times 1/4 is 1, and y to the 2nd power, because 8 times 1/4 is 2. Moving on to number 13. Get a few more pieces here. Remember to think of the 16, the k, and the m really as different pieces, because they're all different factors in that product. Now we do have another negative exponent. You could take care of that now or later. I think I'm going to opt for just doing that later. We would have a 16 to the 1/4 power, k to the 4th to the 1/4 power, and m to the negative 8th to the 1/4 power. And there's certainly different ways you could look at this. 16 to the 1/4 is the same as the 4th root of 16, which is 2. K to the 4th to the 1/4, again, that's that power of a power property, so we multiply those exponents together, we get k to the 1st power, and then the m, the same thing, and multiply the negative 8 by the 1/4, because it's a power of a power, we get m to the negative 2. Now I need to take care of that negative exponent, so the 2 and the k stay on top because they do not have negative exponents. The m moves to the denominator, or m squared really, because it does have a negative exponent. And so that's what number 13 ends up to look like. Alright, for number 14, we are going to write this with rational exponents in order to get started and apply those properties for exponents. Again, we are assuming that all radicands represent positive real numbers, and they want the answers in exponential form. So again, this time they are asking for the answers in exponential form, so we can certainly do that. Switching this to rational exponents, the 6th root of w would be w to the 1/6 power, and then the cube root of that would mean to the 1/3 power. And then we really have a power of a power property, so we multiply the 1/6 by the 1/3, and we end up with 1/18. So w to the 1/18th, and again, remember they did ask for the answer in exponential form, so we can leave it like that. And that is the end of our quiz, so hopefully this was helpful, and thanks for watching.